Next we have exercise 24. This one is a long one. Long one means the statement is long. First, the exercise talks about a theorem without talking about its proof. That theorem or that result is going to be assumed, and then we have to use that result to prove something else. Let's see. Suppose we know the following theorem. If psi is an automorphism of the matrix algebra Fn, this means that psi is a homomorphism of Fn and psi is bijective, 1, 1 and onto. And being a homomorphism, of course, means this, that psi respects addition of matrices and multiplication of matrices, where the matrices, of course, are coming from the matrix algebra Fn. And there is an additional condition imposed on psi as well, this, that if you apply psi on lambda, where lambda is a scalar matrix, then you get lambda back. Psi fixes every scalar matrix. You do recall that we have decided to, long ago we decided to denote the scalar matrix, all of whose diagonal elements are equal to the scalar lambda, by lambda itself. Instead of writing lambda times I or lambda times 1, we simply write lambda, and when we treat lambda as a matrix, it's that scalar matrix, all of whose diagonal entries are lambda. So it's that thing. If all these things are true about psi, then there exists a matrix P in Fn which in fact is invertible, such that A psi is equal to PA P inverse for every matrix A in Fn. We have to assume that this is true. And now what is it that we have to prove using this result? This thing. If star is an adjoint on Fn which fixes every scalar matrix lambda, just like psi, then there exists a P in Fn for which something happens. Okay, I ran out of space, so now let me complete this. So then the missing part is this, that if all these things happen, all these things are true, then there exists a matrix P in Fn, an invertible matrix P, for which the adjoint of A is equal to P times A transpose times P inverse for all matrices A in Fn. And additionally, the matrix P inverse times P transpose is a scalar matrix. So let's see the solution. So we start the solution by defining a new function psi from Fn to Fn, like this. Psi maps every matrix A onto the transpose of its adjoint. And this adjoint, of course, is the adjoint that we have in the statement of the problem. Note that this psi is the composition of these two functions, a transpose and adjoint, both of which are well-defined functions from Fn to Fn. So obviously the composition is also well-defined, so that means psi is well-defined. And then there is something for you to do. One can verify that psi is bijective homomorphism. To show that psi is a homomorphism, you proceed exactly similar to what we did in the previous video. Do you remember that in the previous video we encountered a composition of two adjoints. One of them was some adjoint star and the other one was some other adjoint. Not necessarily different, but some other adjoint which we denoted by star within a circle. So you proceed exactly like that to show that this psi is also a homomorphism, and using properties of transpose and the conditions in the definition of a general adjoint star, it's a very easy task to show that psi is bijective. Alright, so that means psi is a bijective homomorphism now. And what is the effect of psi on scalar matrices? Let us next see that. Say lambda is a scalar matrix in Fn, of course, that's understood, and we apply psi on lambda. So that means we get lambda star transpose. Already it was given in the problem itself that lambda star is equal to lambda because our star fixes every scalar matrix. So that means you are looking at the transpose of a scalar matrix, which is lambda itself. If you take transpose, what do? You interchange rows and columns. That has no effect on not just scalar matrices but in general diagonal matrices. So nothing changes. So that way psi also fixes every scalar matrix. But then we can apply the theorem that is given in the problem. By that theorem, there exists a matrix P1 in Fn. This is not quite the P that we want there. Okay, so we are calling it P1. You can call it something else also, say Q. An invertible matrix P1 in Fn such that A psi is equal to P1 A P1 inverse for all A belonging to Fn. Okay, so far it's not really that complicated, but we haven't got what we really want. But now let us see how exactly this psi is going to help us getting that. Now next we calculate A adjoint, A star. In its place we can write this because we know that the transpose of a matrix is the matrix itself. Now this thing inside the square brackets is A psi. So A psi transpose. And by what we have found just now, in place of A psi we can put P1A P1 inverse. So the transpose of that. Now if we take transpose of each matrix here, then the order gets flipped. So first you take the transpose of this one, followed by this one, followed by this one. So that's how you get this. P1 inverse transpose, A transpose, P1 transpose. Now you also know that you can interchange transpose and inverse. This is something we saw before also. So in place of P1 inverse transpose, you can also write P1 transpose inverse. And this is already P1 transpose, so you take its inverse and the inverse of that, because these two inverses will cancel and will give you P1 prime, P1 transpose. So do you see now that you have almost got half of your claim? Because you can think of this P1 transpose inverse as a single matrix. Say you can call it P, then this is P inverse. So that way you are getting A star as P A transpose P inverse. So you have found your P. This is your P. Okay, so we write that. Hence with P equal to this, we have A adjoint equal to P A transpose P inverse. But next we have to prove that P inverse P transpose for this P is a scalar matrix. Is it really going to be a scalar matrix for this P? Let's see. Next, let us see another calculation. This time we do not start with adjoint of A but with A itself, and we use this fact. If you go back and see the definition of general adjoint, there this condition that A equals the adjoint of its adjoint is one of the conditions in that definition. So that's how we have this. Now in its place we can write this because of what we have proved just now. I should have actually written now for any A belonging to Fn, but okay, it's understood. It is understood that this fact is true for any matrix A in Fn. In particular, this fact is also true for A transpose. I mean, think of this A transpose itself as a matrix. Let's call it B, say. So here we are looking at B star. So by this fact, we have B star equal to P B transpose P inverse. So that's how we are having this. But then again, in place of A star, you can simply put this. Alright. And do not forget that there is a transpose. And then we apply the transpose. So the order will change. P and P inverse of course will stay in their places. And here we will have the transpose of P inverse followed by the transpose of the transpose of A transpose, followed by the transpose of P. Okay. And now let me keep this as it is, this part P times transpose of P inverse. A transpose becomes A, and in place of this product P transpose times P inverse, I can write P times P transpose inverse inverse. Why? Because if you take inverse on the individual matrices, the order will change. So first you are going to take the inverse of P transpose, which is just this P transpose, and then you take the inverse of P, which is here. So that means yes, this is equal to this. But then where do we go from here? Although the calculation stops here momentarily, but we continue the statement. Okay, we see that these things happen, comma, which implies this. What are we doing here? You see this inverse, we have multiplied both sides of this equation from the right side by this product, so that on this side the product and its inverse cancel each other, and we are left with this P times P inverse transpose A. P times P inverse transpose A. We have deliberately kept this part separately within square brackets. And what will happen on this side? What have we done just now? We have multiplied both sides of this equation from the right by this P times P transpose inverse. So that you will do on this side also, A times that, A times P transpose inverse. But then again you know that you can interchange inverse and transpose. So you next write in place of this P times P inverse transpose. Now you are looking at a very interesting thing here. The matrix, you can see that these are the same matrix. Okay, P times P inverse transpose, that commutes with A. That matrix times A is equal to A times that matrix. The interesting thing here is that this is true for all A, for any matrix A in the algebra Fn. And when you encountered a matrix which commutes with every matrix of Fn, then that is a very special matrix. We encountered such matrices long ago, and we actually determined precisely what matrices have this property. They are scalar matrices. So from this and a previous exercise, you conclude next that this is a scalar matrix. So next we write just that. Since this is true, that means this thing is true for all A in Fn, it follows from this is the exercise that I was talking about. Exercise 7 of section 6.1, that P times P inverse transpose is a scalar matrix. But then its own transpose is also a scalar matrix, because when you take a scalar matrix and you take its transpose, you again get a scalar matrix. But what is the transpose of this? To calculate that, first you take the transpose of, because the order will change, right? First you take the transpose of this, which is just P inverse, and then you take the transpose of P. And this is what you had to show, that it's a scalar matrix. So this is the second half of this entire claim, and that completes this solution. And let me just end this video here itself. There are a few others still there in this set of exercises that we will solve next week. So see you next week with more solutions. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.